to this, the sharing the screen. So let's hope this works. Okay. All right. It's good morning for me and good day to everyone else. I'm Betty Chen, and I am chairing the SEAMS Most Influential Paper Award. And you'll notice that actually it's for 2 years, 2008 and 2009, neither of which are 10 years prior to this current year, and I will explain that shortly. But first, let me start by acknowledging my committee who helped me with this process to make the selections. Gregor Engels from Paderborn University, Jean-Marc Jezecal from Rennes in France, and Liliana Pasquale from UC Dublin and Lero. So just within the last 3 or 4 years, the SEAMS steering committee has decided that it was high time that we have take a more reflective look on the impact of the papers that have been published and presented in SEAMS. And so in an effort to sort of catch up, to make sure that we were able to capture all of the papers that during the beginning of SEAMS, they put together a phase-in process, if you will. So starting with last year, we were doing 2 MIP awards per year. So 2020, we had MIP awards for 2006 and 2007. And so this year we are awarding papers from SEAMS 2008 and 2009. And so you'll see by the time we get to SEAMS 2024, we will actually be in the 10-year Most Influential Paper Award. So that's just to kind of give you a little bit of background regarding this process. So the steering committee for SEAMS put together a set of selection criteria, and it gets revised each year and updated as appropriate. And so there's 2 big categories for the selection criteria, namely impact and then also professional merit. So the impact is looking at the contributions themselves, how have the results affected the field in terms of the research guidance, as well as the practical use of the research products, and also what kind of transition in terms of the knowledge transfer to the state of the art and hopefully even to the state of the practice. And then from the professional merit side, we're looking at the novelty, creativity, and originality, and also the quality of the research itself, how reproducible it is, etc. So these were the criteria that were considered by the committee as we reviewed the candidates. And so just a brief overview of the selection process itself. So firstly, the data, and that actually obviously is the papers themselves. So both years had 17 papers that were published in the SEAMS proceedings. At that time, we only had full papers. So that's something to note. We also obviously considered citation statistics from multiple sources so that we had make sure that we had good coverage there, and also even references to things like patents. And then independently, the committee members were evaluating all of the data to provide independent evaluations and rankings. And then we performed a vote based on the rankings and the written explanations, justifications, and then we had discussions afterwards to make the final selection. So here's where this drum roll. So both MIP award winners will be giving brief retrospective presentations. They'll be 10 minutes long, each with a 2-minute Q&A afterwards. And so I'm trying to figure out how I could do this to capture what we might do in person. So the MIP award, the 2008 MIP award, I'm extremely pleased to announce that was awarded to paper by Daniel Sykes, William Heaven, Jeff McGee, and Jeff Cromer for their paper called From Goals to Components, a Combined Approach to Self-Management that was presented at SEAMS 2008. This is a variation of the certificate that the authors will be receiving. And the retrospective will be given by Jeff Cromer from Imperial College. So Jeff, I'm going to stop sharing, and so you can start sharing your screen to give your presentation.
Okay, thanks. Let me do share screen.
This is easier than trying to switch dongles, right? If we were live in person, we'd
exactly.
work PC, you know.
Oh, there you are. I presume you can all see that.
Yes.
So first of all, I'd like, on behalf of all my authors, to thank you very much. We're absolutely delighted with receiving this award. It's always nice to have some recognition. And especially, I think MIP awards are wonderful in this respect in terms of actually, it's not gone into garbage. It's actually been read by a few people, which is kind of nice. So I'll talk, it's just a little retrospect, as you say, and talking a little bit about what we call own goals. Going back many years, we've always been interested in change. I think we've been doing work in this area for a long time. First in the sort of domain of distributed systems and dynamic configuration. But then later on, we came more and more into the realms of, rather than manage change and trying to manage the reconfiguration, actually performing this in an adaptive manner. And in 2007, the other Jeff and I basically proposed a 3-layer architecture based on the work of Gat. He was a well-known expert in robotics. And the idea was to move from goals, as it says, down change management into control and provide a sort of separation of concerns, which at the time we felt was not quite there with respect to, say, the MAPE model. So at the top layer, for instance, what we have is goal management. This is where we have a goal hierarchy, what the system is expected to do, and also from those goals to produce, have a domain model and produce plans as to what you want to execute. At the next layer down, then, what you do is you take those plans, and there may be many of them. You decide which of the ones that you select. You assemble all the components that you need in order to actually execute that particular plan, configure them together, and then start the actual process of executing those plans, which is directed from this level. The layer at the bottom then is the actual components. These are the components which execute the actual plans. They also can perform dynamic reconfiguration at the command of the layer above in order if a new plan or something needs to change. And this is basically the 3 layers that we introduced. And as was introduced in the sort of rainbow model of Bradley and David, of course, this is actually interact with the actual environment through sensors and actuators performing, basically sensing events from the environment and performing controls to do this. So with this 3-layer model, what we did in the 2008 paper was actually describing a realization of this to show that it is actually usable in an environment. And at the top layer, what we did was originally we used, in the paper, for instance, we used MVP, which is model-based planning, some work from Trento in Italy. But later on, we found that we could extend label transition systems that essentially, if you distinguish between the controlled actions, which the controller will do the plan, and those which come from the domain, which are uncontrolled, then what you could use an extension of our LTSA model checker based on an algorithm from Amu Pnueli, near Peterman and some others, to actually create a plan, synthesize a plan which ensures that you can satisfy the goals in this environment. At the next level down, we have the actual plan interpreter. This performs the execution, and it's also have an assembler. This is the thing which gathers all of the components together, configures them, ready for execution. And if necessary, as I said, also performs or directs dynamic reconfiguration. And at the lower layer, we had backbone interpreter. This is actually a really nice piece of work from a PhD student of ours called Andrew McVeigh, who's now making lots of money in the games world, which supports the dynamic configuration and the execution. What happens if you get, for instance, unexpected domain behavior, something that you didn't actually expect? Well, what you need to do is to change the domain model. So in 2013, what we did was look at a way of generating revised plans based on changes for the domain model. So you log the execution traces, you have to perform inference on this, and then perform model updates. And we used a probabilistic rule learning system called NOMPROL, which essentially hypothesizes, based on what's happened, hypothesizes what is the best way of explaining what's happened. And that explanation is either in the form of new or modified, revised rules, which you can then put into your domain model. So this was a way of essentially revising our domain model. Based on that, we could then perform controller synthesis and therefore change the system and change what's happening, if necessary, performing dynamic reconfiguration. What was also rather nice about this piece of work is that since these rules are actually readable, you can actually provide feedback to your user in the loop, as was discussed in the last session, giving some idea of what the system's doing. Also, of course, the system designer could direct which of the rules you should use if there's a number of different options. So that was one example of work we've done since based on that. Another one, sorry, I should go on. So as a result of that, we realized we had to elaborate our description of the three-layer model to make more explicit the K part or knowledge part, which is in the MAPE K loop. And so we actually put what we call a knowledge repository on the side to make it explicit that we assume these goal models, domain models, and so on are there, available at runtime, and particularly available for reasoning at runtime. This is very important. Another piece of work which we've done recently, which won actually the best paper, was assured and direct dynamic update of controllers. This is actually a piece of work, funny enough, based on some work that Betty and her colleagues did in performing dynamic change. And my colleague, Sebastian Uchitel, is busy having fun with drone experiments in Patagonia. And this is actually a trace from one of these where we have a change of goal, where the drone was doing the red bit over here, gets an instruction with a change of mission, does an interim change during the reconfiguration, and then starts to perform a whole new plan, which is direct shown as its path in blue here. And this was just, again, an indication that the work is actually useful. But I have to say that, of course, like all pieces of work, not everything has been successful. Playing with robotics is not necessarily successful. This is one of the example of one of our own goals. We've had a lot of fun and we've had a lot of mistakes as well. So where are we now? What are we doing now? Well, we're all doing our own individual things. Daniel is actually a principal software engineer at Ocado. For those who don't know, Ocado is probably the biggest online grocery shopping distributor, I think, certainly in the UK, and is now actually exporting its technology, which these are all little robots on a grid which move around, and they're exporting this technology, I think, also to the States and to other places. And Daniel actually has been working there for a number of years. This is a description of it essentially with these 3,000, there's a huge number of robots essentially controlled centrally in the system. What's happened to Will? Well, Will's now senior editor for AI at MIT Technology Review. He actually wrote this piece about the Ocado system that Daniel works on, and wrote this lovely piece about his experience of working with us at Imperial College. Very complimentary, I must say. And Jeff, my other Jeff, well, Jeff is actually having fun sailing, as it says, fishing and hacking mobile phones and smart watches at the moment, and seems very relaxed whenever I speak to him or manage to see him. What about me? Well, I'm still hanging in there. I'm still very interested in how to formulate faithful domain models. Been looking at this. Basically, everything has to be available at runtime, to support reasoning at runtime, revision at runtime, and here we're using a different form of machine learning, basically ILP, inductive logic programming, and variations of that to try to reason about what's happening, and use that as the basis for controller synthesis. And all of this is in an iterative process that we're looking at, because basically in the end, what we're trying to perform is RE at runtime. This actually is the major challenge, and this is where we're at. And this is being done in collaboration with my colleague, Sebastian Uchitel and Dalal Al-Raja. So I'm sorry I had to rush through all of that, but if you're still out there listening, thanks very much for listening. And thanks very much for the award. We really are delighted.
Thank you. Clap for everybody.
Thanks,
so,
Betty.
Yes, that was perfect. I should have known that a requirements person would end exactly at 10 minutes, which is the time. So the goal was there, and the change management. So I guess first I will see if the audience has any questions. I didn't post anything in the chat, but we're a small enough group that if you have a question, to maybe shout it out. Otherwise, I have a question, but any questions? So Jeff, I really found it fascinating that, that vision that you had, actually starting with the FOSS paper and then also realized with this current paper, has really kind of stood the test of time. And obviously that's the notion of that's getting awarded the MIP. But I'm curious about if there were two things. One, if there was one specific key insight that you felt that you had as part of your SEAMS paper from 2008, that you felt like that was sort of almost like the holy grail that really kind of helped to open up this whole area of research, that obviously there have been a lot of people who've also followed along this line of research. And then I'll just give you the yin and the yang. The other part of it is that now looking back of having done all this research, especially in the controller synthesis, if there was one area that you thought, I would do that, this is one thing I would do differently, having seen what I've seen.
That is actually a really hard thing to do. I would have, since we always think we're perfect and I couldn't possibly have made any mistakes. I think one of the things which worked well and which we did learn was the separation of concerns that provided allowed us to work on pieces of the whole system, to concentrate on that and try to make a contribution in each of these different areas, rather than trying to build yet another new system, with everything mixed up. And I think the separation of concerns allows also, hopefully, others to pick up a piece of technology or to basically do something better and to replace it. So it provided us with a nice architecture, framework, and I think the experience of the 2008 was that we could actually do that. Could we do something better? I think that we didn't perhaps realize just how difficult it was all going to be. I think that the notion of trying to deal, particularly in online systems, with anything, with real time, I should say, with anything which is totally automatic, and then to interact with the real world, such as robots, as you can see, was actually extremely, extremely difficult. And having just recently listened to a talk from somebody from NASA, I'll try to keep this brief, what you realize is just how careful they are about making sure that each and every part works. They have, by the way, no adaptive system. I mean, that everything is built in, and if they need to, they will actually have to reload new software. But everything is so carefully planned, and so getting everything right and understanding the domain, especially when you go in space, must be extremely difficult. So it doesn't answer your question properly, I realize, but that's it anyway. Right. It's hard. It's hard. It's very hard.
I remember doing a stand at NASA JPL, and they even verify the compilers, right? That they compile the code that gets loaded on. So yeah. So thank you very much, Jeff. That was wonderful. Actually, that was very insightful as well. So again, let me thank you and congratulate your team for your work.
Thank you. Thanks. It's really and all the co-authors. Thanks.